Now, a big area where exponential functions are utilized is in calculating compound interest. Now, one of the things I don't like about your textbook is that they often use situations like this. Um, Instead of defining a variable and being consistent, they often, use notation like this and then give a formula with variables that follow it. Not a big fan of that, and you're going to see me at times putting in a formula that is commonly seen over most other textbooks. Um, but the compound interest here is that we're trying to compute like interest based off of like the fact that many times when they're computing interest, they'll take your interest rate, which is a nominal interest rate, and then they'll compound it by, they say they compound it quarterly. They basically take that interest rate divided by 4 and then apply that interest at 4 times during the course of the year. As a result of that, I mean, if you tend to compound the interest, so if I had used like 8% interest, just once annually and 8% interest compounded quarterly, I'll tend to get a little bit more money with compounding it quarterly because of the fact that, each time I take the next quarter of a percentage, I'm taking it off of the previous amount, which has already been risen since the first time. So that's kind of how it works. And so they give you a general formula like this, but the formula that we're going to be using here, I've seen some textbooks and most textbooks, they use different letters, for what they're representing as N, as M here, but I've seen it written as A, which is your final amount after a period of time, equals P times 1 plus R. Now here they're saying that M is the number of periods per year. That's why some textbooks will write it as N to the NT power. I'm okay using the letter M instead of N. It doesn't make a difference to me. But I would say, like, make sure you realize that we're going to be using this because your textbook makes another thing that stems from this seem a little bit more difficult than it needs to be. And that's when we eventually get into present value. But we'll go talk about that in a moment. So, so an example here: find the value of $4,000 invested for 2 years at 12% interest compounded quarterly. So I just have to make sure I put these things in the right places. So my starting amount is my principal. That's P. I'm going to take the 12%. Now notice they're writing it as a decimal. Okay, so make sure that you're, realizing that we're basically looking at this as 12 over 100 for the percentage, and that's what goes here. This is the number of times we compound it in a year, so or compounding periods in a year. So that's what M is. So that's what 4 is, and of course the time is 2 years. So that's how we're getting this plugged in. And it's basically, at this point, a plug-and-chug problem where it says, okay, here's all the numbers, put them in the right places, and churn out the answer. So in this case here, I would get 4,000 times 1.03 to the 8th power, which is about $5,067.08. So after 2 years, that's how much is going to be there. And now, again, as we're doing this, we're also assuming that we're not putting additional money into whatever this is, whether it's some kind of money market account or a bank account, whatever the case may be. So let's have you try it now, using some of the words, so you get a chance to see some of the words that will often be dealt with when dealing with compound interest. How much will an initial investment of $5,000 is 6.9% APR, which is annual percentage rate, and that's not 100% accurate. We'll just say interest, because an annual percentage rate is actually different than the nominal rate, because I mean an annual percentage rate is, I mean, if I take 6.9 and compound it anything but annually, I'm going to have a slightly different value for the annual percentage rate than the actual, 6.9%. So, but how much will it be worth in 10 years if, and you see down the line, A is compounded annually, B semi-annually, C is quarterly, monthly, daily, and hourly. Some of these are a little bit strange, and you probably won't see any kind of accounts that work with that kind of number of times compounding, but this is how you would calculate that. So take a moment and answer these questions, and then we'll go over it. Okay, so again, all we're going to be doing is using the formula A equals P times 1 plus R over M to the MT power. And really the only thing that's going to be changing differently in each one of these problems, I mean, this, and this are going to remain the same, namely $5,000, 0.069, and 10. It's going to be these two guys that are changing through the course of this problem. And we just want to get an idea of how just changing that portion of it is going to affect these answers. So the first one I see is when I plug $5,000 and do it annually, I get about $9,744.22. So if I'm doing 6.9% each year for 10 years, just once a year, that's how much I'm going to get. Now, if I take that percentage rate and compound it semi-annually, which means twice in a given year, so essentially I would take that 6.9% or 3.45% and apply that to the $5,000 midway through the year, and then towards the end of the year, apply another 3.45% to the new amount that I had grown from before. So when I do that, essentially, and use this formula, I get $9,853.26. So basically at this point, we have a difference of, just so I do it in my head here, about $109.04. So I mean, so that's pretty noticeable. So will I have such a noticeable result if I go from semi-annually to quarterly? Where again, quarterly means I am going to be taking this interest and splitting it into 4 pieces and then apply it 4 times during the course of the year. When I do that, I get $9,910.10. So you can still see it's going higher because that's definitely noticeable. But this time around, I only went up $56.84. So it's not nearly as much of a rise as I went from annually to semi-annually. If I compare annually to quarterly, oh yes, it's still a pretty big difference. But the one thing you're going to keep noticing is that ultimately the number of times you compound that interest is going to have it's going to have an effect, but how big that effect is going to be is going to dwindle depending on how many times you're compounding that interest. So if I go down and now do monthly, where M is now 12, I would get $9,948.90. So you can see now we're going from quarterly, which is just 4 times a year, to monthly, which is compounding at 12 times a year. I'm only getting a difference of about $38.80. If I compound it daily, now we're just saying there's 365 days in a year. I mean, I guess technically you could say 365.25 in any given year because of leap years and all that stuff, but we'll just say 365. I get about $9,967.93. So at this point, I'm getting about $19 and some change, maybe a little $18 and some change. Let's see. Let's do a quick calculation here. $19.03 difference. So as you can see, again, it did go up again, but the amount it went up when I went from monthly to daily was not as much as whenever I went up from annually to semi-annually. And then lastly, hourly. There are 8,760 hours in a year approximately. Again, that's 365 times 24. So when I apply that, I get $9,968.55. So now, I mean, we're talking about a difference of maybe $1.42 between compounding it daily and hourly. And the reason being for that is, well, yes, if I'm compounding it more often, but I'm also taking that interest rate and I'm splitting it into even smaller pieces. So, that's going to have an effect, on the overall outcome as well. So those are the solutions to these. We'll look at another situation a little bit later in these other future slides, but for the time being, that's all I have for now. Have a good day and move on to the next example.